Callisto, Jupiter's second largest moon and the third largest moon in our solar system, shares a similar size with Mercury. Historically, some scientists dismiss Callisto as an unremarkable, ugly duckling moon, often describing it as nothing more than a chunk of rock and ice. This perception stemmed from its heavily cratered surface, devoid of any apparent geological activity, such as active volcanoes or tectonic plate movement. However, in the 1990s, data collected by NASA's Galileo spacecraft unveiled a tantalizing secret hidden beneath Callisto's facade, a concealed salty ocean beneath its outer shell. This discovery propelled the once deemed lifeless moon onto the list of celestial bodies that could potentially support life. Callisto was first observed on January 7, 1610, by the Italian scientist Galileo Galilei, who also discovered Jupiter's three other largest moons, Ganymede, Europa, and Io. The moon derives its name from Greek mythology, where Callisto was a woman transformed into a bear by Zeus. It's worth noting that Zeus is the Greek counterpart to the Roman god Jupiter. Callisto holds the distinction of being Jupiter's second largest moon, surpassed only by Ganymede, and ranks as the third largest moon within our solar system. Its size is nearly on par with that of Mercury. To provide some perspective, Callisto boasts a circumference of approximately 9,410 miles at its equator. This moon follows an orbit around Jupiter, situated at a distance of roughly 1,170,000 miles from the gas giant. Additionally, it's noteworthy that Jupiter, in turn, orbits the Sun at an approximate distance of 484 million miles. Callisto maintains an orbit around Jupiter at a distance of approximately 1,170,000 miles and completes a single orbit around Jupiter in about 17 Earth days. Notably, Callisto is in a state of tidal locking with Jupiter, resulting in the same side of Callisto, consistently facing the gas giant in terms of its orbital position relative to Jupiter's other major moons. Callisto is positioned about 1.8 times farther from Jupiter than Ganymede, to 0.8 times farther than Europa, and a significant 4.5 times farther than Io, which is Jupiter's closest large moon. Jupiter, along with its entourage of moons, orbits the Sun at an approximate distance of 484 million miles. The entire Jovian system, comprising Jupiter and all of its moons, takes about 12 Earth years to complete one full orbit around the Sun. Callisto's surface is predominantly icy and adorned with a variety of craters, ranging in shapes and sizes. These craters include bowl-shaped formations and craters with multiple concentric rings. Insights gathered from data collected by the Galileo spacecraft suggest the intriguing possibility of a subsurface ocean within Callisto. Scientists estimate that this potential ocean may lie approximately 155 miles beneath the moon's surface. However, more recent research has introduced some uncertainty. It's now suggested that this ocean might be situated even deeper below the surface than initially believed, or, alternatively, it might not exist at all. If indeed present, this ocean could potentially interact with rocks, raising the intriguing possibility that Callisto could harbor conditions conducive to life. Internally, Callisto may possess layers comprised of ice, rock, and even traces of metal. These layers could extend toward the moon's center, contributing to the complex and enigmatic composition of this Jovian moon. Callisto's surface presents a unique geological history. Within our solar system, it stands as the oldest and most extensively cratered surface known, with an estimated age of around 4 billion years. This lunar landscape has endured relentless bombardment, likely from comets and asteroids over the eons. The enduring presence of these impact craters serves as compelling evidence for the Moon's relative geological quiescence. Unlike other celestial bodies, Callisto lacks active volcanoes or tectonic activity that would otherwise erase or modify these craters. As a result, Callisto's surface exhibits a distinctive appearance, resembling a landscape adorned with bright white dots. These dots are believed to be the peaks of the ancient craters, cloaked with a veneer of water ice, creating a visually striking and enduring testament to the Moon's tumultuous cosmic history. In 1999, scientists made a noteworthy announcement based on observations made by the Galileo spacecraft. During its 1997 mission, they reported the detection of an exceedingly thin carbon dioxide exosphere, which can be described as an incredibly tenuous atmosphere enveloping Callisto. Furthermore, more recent research has unveiled additional findings, indicating the presence of both oxygen and hydrogen within Callisto's exosphere. These discoveries shed further light on the intriguing and complex composition of the Moon's exospheric environment. Callisto has earned a place on the list of celestial bodies within our solar system that are considered potential havens for life beyond Earth. Data collected by the Galileo spacecraft, coupled with scientific modeling, has suggested the tantalizing possibility that Callisto may harbor a salty ocean beneath its surface. This ocean appears to interact with a layer of rocks located approximately 155 miles beneath the Moon's exterior. These conditions, the presence of liquid water and interactions with rocks, are regarded as key ingredients that could potentially foster the creation of life. Furthermore, the detection of oxygen in Callisto's exosphere adds another layer of intrigue. Oxygen is often considered a potential indicator of life, heightening the interest and curiosity surrounding the Moon's potential habitability. The subsurface oceans beneath these moons are believed to be quite extensive, stretching across the entire circumference of the moons and reaching depths of tens of kilometers. However, they face a significant challenge for scientific study, because they are encased under layers of ice that are also tens of kilometers thick. This icy barrier makes it exceptionally challenging to conduct research and gain deeper insights into these hidden oceans. One of the most promising methods we've employed in our quest to understand these subsurface oceans is to examine how the salt content within these oceans affects their electrical conductivity. We do this by analyzing the magnetic fields surrounding these moons. However, as noted by Professor Joachim Saul, a planetary scientist from the University of Cologne in Germany, these studies have often overlooked other factors that can generate magnetic fields. For instance, the presence of thin atmospheres around the moons can also contribute to magnetic field effects. Therefore, it's crucial for us to carefully distinguish and isolate the magnetic field effects that genuinely originate from the subsurface oceans, allowing us to gain more accurate insights into their properties.